In this lesson, we'll continue our look at enolate chemistry, focusing on the Clyzen condensation, Michael addition, and related reactions. First, we have the Clyzen condensation, which is the reaction of an enolized ester with another ester. The reaction results in the formation of a new carbon-carbon bond, producing a beta-keto ester. In the example, we see ethyl acetate undergoing a Clyzen condensation via enolization with ethoxide. The base that's used to induce enolization is often matched to the alkoxy group of the ester. This prevents formation of byproducts introduced from direct acyl substitution reactions on the ester. The reaction mechanism is just base-promoted enolization followed by acyl substitution. In the first step, the base removes an alpha proton from the carbonyl. In the second step, the resulting enolate attacks the unenolized ester, initiating an acyl substitution. In the last step, the carbonyl pi bond is reformed and the alkoxide expelled to give the final product. Claisen condensations can also occur between two different esters. In a mixed Claisen condensation, one ester is enolized and a second, different ester then acts as the electrophile. Just as we saw with mixed aldol reactions, mixed Claisen condensations can result in a complex mixture of products. One solution is to perform the reaction with only one enolizable ester. In the example, we see ethyl benzoate reacting with ethyl acetate in a Cleison condensation. In this case, only the ethyl acetate can form an enolate. The ethyl benzoate doesn't have any alpha protons and can't be enolized. Just as with mixed aldol reactions, a more general solution is to pretreat one ester with a strong kinetic base such as LDA and react the resulting enolate with a second ester. Here, we see methyl acetate treated with LDA, which quantitatively converts the ester into its enolate. After enolization, methyl propanoate is added as the electrophile, giving essentially only one product at the end of the reaction. The Clyzen condensation can also occur intramolecularly on compounds with two esters. The intramolecular Clyzen condensation is known as the Dieckmann cyclization, and as the name implies, the reaction results in the formation of a ring. In the example, we see a 6-carbon diester undergoing a Dieckmann cyclization. In this case, the reaction forms a new cyclopentanone ring. The Dieckmann cyclization is useful for forming substituted cyclopentanones and cyclohexanones from 1,6 and 1,7 diesters. Enolates can also be used as nucleophiles in the conjugate addition to alpha-beta unsaturated carbonyls. The Michael addition is just that, the conjugate addition of an enolate to an alpha-beta unsaturated carbonyl. Remember that most alpha-beta unsaturated carbonyls can undergo both direct attack at the carbonyl and conjugate attack at the beta carbon. Using a highly stabilized enolate, like those flanked by two carbonyls, enhances the selectivity for conjugate attack. In the example, we see 3-butene-2-one undergoing Michael addition with dimethylmalonate using methoxide as the base. The reaction mechanism is simply a base-promoted enolization followed by conjugate addition. In the first step, the base removes one of the acidic methylene protons from the dicarbonyl. The resulting enolate then attacks the beta carbon of the alpha-beta unsaturated carbonyl. In the last step, the resulting enolate is then protonated on the alpha carbon to give the final product. We'll wrap things up with a brief look at the Robinson annulation. The Robinson annulation is simply a Michael addition followed by an intramolecular aldol condensation. The reaction results in the formation of a substituted cyclohexenone. In the example, we see 3-butene-2-one undergoing a Robinson annulation with 2,4-pentane dione using hydroxide as the base. The Robinson annulation is just the sequential combination of two reactions you've seen previously, Michael addition and aldol condensation. Fortunately, this means that the reaction mechanism is just the sum of those two reactions.